Title: MoFO. Momentum Filtered Optimizer for Mitigating Forgetting in LLM Fine-Tuning. Abstract: This paper proposes a new fine-tuning algorithm, Momentum Filtered Optimizer, MoFO, to address the issue of forgetting pre-training knowledge in large language models, LLMs. Unlike existing methods, MoFO does not require access to pre-training data and does not alter the original loss function. It iteratively selects and updates the model parameters with the largest momentum magnitudes, achieving similar fine-tuning performance while keeping parameters closer to the pre-trained model. Introduction. Large language models, LLMs, have demonstrated remarkable capabilities in various tasks. However, during fine-tuning, LLMs may forget the knowledge acquired in pre-training, leading to a decline in general capabilities. This paper aims to mitigate this issue by proposing MoFO. Motivation. The fine-tuning loss of LLMs has many minima, and these minima can vary significantly in their distances to the pre-trained model. The authors observe that minima closer to the pre-trained model are less likely to experience forgetting. Inspired by this observation, MoFO manages to approach closer minima by dynamically updating a portion of parameters that are most effective for reducing fine-tuning loss at each iteration. MoFO algorithm. MoFO is a replay-free and regularization-free method that iteratively selects and updates only the parameters with the top alpha% largest momentum magnitudes within each block. The blocks refer to the parameters of different parts of the network, e.g., weight matrices and bias terms. Contributions. The authors propose the MoFO algorithm, a new optimization method designed to mitigate the forgetting of pre-training knowledge during the fine-tuning process. They present an initial convergence analysis of the MoFO algorithm and conduct experiments on various tasks, demonstrating that MoFO outperforms existing methods both in fine-tuning performance and mitigating forgetting. Overall, MoFO is a novel approach that addresses the issue of forgetting in LLM fine-tuning without requiring access to pre-training data or altering the original loss function. It has the potential to enhance the performance and generalizability of LLMs in various tasks. The paper discusses the issue of catastrophic forgetting in fine-tuning pre-trained models, particularly Pythia 160 meters, using the Atom optimizer. It presents a novel approach to mitigate this problem by modifying the Atom optimizer to update only the subset of parameters with the largest momentum magnitude. This new method, called Momentum Filtered Optimizer, MoFO, is designed to keep the model closer to the pre-trained model during fine-tuning, thereby reducing forgetting. The authors first analyzed the loss landscapes of Pythia 160 meters after fine-tuning on a subset of the Flan dataset using both Atom and Lion optimizers. They find that the two training methods converge to different minima with similar fine-tuning loss, but Lion converges to a minimum that is significantly farther from the pre-trained model and archives a much larger pre-training loss. The authors then discuss how to keep the model closer to the pre-trained model by using the classical block coordinate descent (BCD) method. They propose updating only the parameters with the greatest influence on reducing fine-tuning loss, measured by the magnitude of its gradient. However, in the Atom optimizer, momentum directly affects parameter updates, while gradients influence parameter updates indirectly by affecting the momentum. Motivated by these discussions, the authors design MoFO, which modifies the Atom optimizer by updating the subset of parameters with the largest momentum magnitude. MoFO partitions all parameters into fixed parts according to the network architecture and selects alpha% of the parameter entries for BCD update within each part. The authors formally introduce MoFO in Algorithm 1 and illustrate its mechanism in Figure 2. They note that MoFO efficiently selects and updates the most influential parameters, as dictated by the momentum's magnitude, thus enhancing the fine-tuning process while alleviating the catastrophic forgetting of pre-training knowledge. The paper discusses the optimization of fine-tuning large language models, LLMs, to mitigate catastrophic forgetting. It introduces MoFO, a novel optimization algorithm that significantly reduces the amount of parameter movement during fine-tuning, thereby preserving the pre-training knowledge. The authors demonstrate the effectiveness of MoFO by comparing it with the Atom optimizer on various common-sense tasks and pre-training loss landscapes. The MoFo algorithm is based on a momentum-based optimization method that utilizes a filtering strategy to select the top alpha % of gradients for updating the model parameters. This filtering strategy helps in reducing the noise in the gradients and thus leads to a more stable optimization process. The authors also provide a simplified version of MoFo as a variant of gradient descent, GD, and prove its convergence. The paper presents experimental results on instruction fine-tuning and continual fine-tuning using Llama 27B and Tiny Llama 1.1b as base models. The datasets used for instruction fine-tuning include MetaMath QA and Code Alpaca, which cover question-answer pairs from different domains like mathematical reasoning and code generation. The results show that MoFo significantly mitigates catastrophic forgetting and improves the performance of LLMs on these tasks. In conclusion, the paper proposes MoFo, a novel optimization algorithm for fine-tuning LLMs, and demonstrates its effectiveness in mitigating catastrophic forgetting. The authors provide theoretical support for MoFo's convergence and present experimental results on various fine-tuning tasks. This work contributes to the development of more efficient and effective optimization methods for large language models. The paper discusses the MoFo approach for fine-tuning large language models, LLMs, to preserve their general capabilities while learning new tasks. It introduces a set of widely used benchmarks to assess the performance and catastrophic forgetting effects on LLMs after instruction fine-tuning. These benchmarks include MMLU, Common Sense, GSM-8K, and Human Eval. The paper also presents two key metrics for continual learning: overall performance, OP, and backward transfer, BWT. The MoFo algorithm is compared with several baseline methods, such as full fort, L2 regularization, L1 regularization, and half fine-tuning, HFT. The results show that MoFo achieves comparable performance in the math task, while significantly mitigating catastrophic forgetting of general capabilities. Specifically, full FT shows a decline of 5% in MMLU accuracy, while HFT experiences a drop of 0.6% in Human Eval. In contrast, MoFo not only maintains but slightly improves these general capability metrics by an average of 0.4%. Compared to L1 and L2 regularization, MoFo significantly outperforms these baselines on GSM-8K by more than 3.2% and 8.7%, respectively. Additionally, while L1 and L2 regularizations suffer from significant catastrophic forgetting on MMLU, MoFo shows no decline. The paper also presents the results of fine-tuning on Code Alpaca using various baseline methods and discusses the experimental results on coding generation and general capabilities. Overall, the MoFo approach demonstrates its effectiveness in preserving general capabilities while learning new tasks, making it a promising method for fine-tuning LLMs. The paper discusses the issue of catastrophic forgetting in large language models, LLMs, during fine-tuning on new tasks. It proposes a novel algorithm called MoFo, which aims to mitigate this problem by optimizing only a fraction of the model's parameters during each update. The authors evaluate MoFo on various benchmarks and compare it with other methods such as full fort, HFT, L1 regularization, and L2 regularization. In the coding generation task, MoFo achieves comparable performance to L1 regularization and outperforms full fort, HFT, and L2 regularization by more than 3% on Human Eval accuracy. It also shows the least degradation in general capabilities compared to other baselines, with an average accuracy reduction of only 1.1%. In the continual fine-tuning experiment on the trace benchmark, MoFo outperforms full FT and HFT by at least 1.4% on the OP score and by at least 4.7% on the BWT score. Combining MoFo with traditional continual learning methods like replay and GEM further enhances performance. The paper also conducts a further analysis of MoFo, investigating the impact of the update fraction of parameters and exploring different update strategies within MoFo. The results show that with a moderate parameter update fraction, MoFo can preserve pre-training knowledge and significantly enhance fine-tuning performance. The paper discusses the impact of update fraction of parameters in MoFo, a method designed to mitigate catastrophic forgetting in large language models, LLMs, during fine-tuning. The authors fine-tune Llama 27B on the MetaMath QA dataset using MoFO with varying update fractions of parameters at each iteration for 2 epochs. They find that larger update fractions can improve MoFO's optimization effectiveness, but also lead to a decline in general capabilities when exceeding 20%. MoFO can preserve pre-training knowledge and significantly enhance fine-tuning performance by choosing a moderate update fraction. The authors also compare MoFO with 2 other BCD methods, randomized BCD and gradient-filtered BCD, in terms of performance on the math reasoning task, GSM-8K, and accuracy changes of general capabilities. MoFO significantly surpasses both gradient-filtered BCD and randomized BCD, indicating that updating parameters with the largest momentum leads to strong optimization power. Furthermore, the paper proposes a toy example to explain why MoFO converges closer to the pre-trained LLMs than those of Atom. In this example, MoFO converges to a minimum closest to the pre-trained model, with a low pre-training loss. This demonstrates that MoFO can mitigate forgetting by reducing interference among attractors and allowing the model to converge to a closer minimum. Finally, the paper reviews related works on catastrophic forgetting, particularly in the context of LLMs, and highlights the growing body of recent works focusing on the forgetting of models' knowledge during the fine-tuning process. Researchers have proposed numerous methods to alleviate forgetting in continual learning, which involves learning a sequence of tasks. These methods are not limited to learning in a sequential manner and can be applied to broader paradigms. Generally, 3 primary approaches are used: replay-based methods, regularization-based methods, and architecture-based methods. Replay-based methods leverage past experiences to facilitate the learning of new tasks. The most straightforward implementation of this approach is experience replay, which involves maintaining old samples in a buffer and replaying them during incremental training. Several other variants utilize gradient information from past tasks. In LLMs, several works propose replay-based methods to mitigate forgetting. Regularization-based methods introduce constraints to preserve old knowledge. Several studies add regularization terms to the loss functions to penalize parameter changes and mitigate forgetting. Unlike these approaches, MoFO does not modify the loss function, and as a result, MoFO reached better fine-tuning performance. Architecture-based methods balance the goals of learning new knowledge and keeping the old one through model architectural modifications. LoRa, as the most popular parameter-efficient fine-tuning (PEFT) methods, modifies the model architecture by freezing the pre-training weights and introducing low-ranked trainable matrices. Empirical work shows that LoRa forgets less but learns less during fine-tuning. Some variants of LoRa find applications in continual learning of LLMs. In comparison, our MoFO still allows for high-rank updates to achieve better fine-tuning performance. Another line of architecture-based methods focuses on model merging. The ideas stem from the understanding that the task-specific knowledge is located at a small subspace of the weight space. Consequently, various model merging methods have been proposed to simultaneously retain pre-training knowledge and improve fine-tuning task performance. However, these methods require an additional post-fine-tuning process before model merging. In contrast, our method only requires one fine-tuning stage. Block coordinate descent, BCD, involves iteratively optimizing over a block of coordinates while holding the others constant. The foundational work of Zhang provides a comprehensive analysis of the convergence properties of BCD under certain conditions. Subsequent research has explored various BCD variants, including randomized BCD, cyclic BCD, and greedy BCD. Among these, the greedy variant, also known as Gauss-Southwell BCD method, has drawn attention due to its ability to prioritize coordinates that yield the most substantial improvement in each iteration, thereby potentially accelerating convergence. In the realm of machine learning, BCD has also found applications. For example, Luo et al. Leverage BCD to perform memory-efficient fine-tuning of LLM, and Xu and Zhang use random masking to perform this. In federated learning, Rothschild et al. Adopts top momentum value unsketch rather than our top momentum filtering to tackle communication bottleneck and convergence issues. A recent work, Wei et al. Addresses catastrophic forgetting during fine-tuning of LLMs by selectively freezing half of the parameters during training. Our approach is akin to a more efficient greedy BCD, achieving superior performance in fine-tuning tasks and alleviating forgetting better. The paper discusses the issue of catastrophic forgetting in large language models during fine-tuning, which is a common problem in machine learning. This occurs when a model forgets previously learned information as it adapts to new tasks. The authors propose several techniques to mitigate this issue, including using a combination of pre-training and fine-tuning, applying different learning rates for different layers, and utilizing knowledge distillation. They also explore the use of gradient episodic memory for continual learning, which involves storing and replaying gradients from previous tasks to prevent forgetting. Additionally, they discuss the importance of maintaining plasticity via regenerative regularization, which helps to keep the model adaptable without losing its ability to learn new information. Furthermore, the paper highlights the significance of understanding the trade-off between generality and speciality in fine-tuning foundation models. It emphasizes that while general capabilities are essential for domain-specific models, they should not come at the expense of forgetting previously learned knowledge. The authors also provide an extensive review of existing literature on catastrophic forgetting, including various methods proposed to address this issue, such as maintaining plasticity, using gradient episodic memory, and applying different learning rates. They emphasize the need for further research in this area to develop more effective techniques for mitigating catastrophic forgetting in large language models. Overall, the paper presents a comprehensive analysis of the problem of catastrophic forgetting in large language models and proposes several strategies to address this issue. It underscores the importance of balancing generality and speciality in fine-tuning foundation models and calls for continued research in this area to improve the performance of these models. The pages from the research paper provide a comprehensive overview of various techniques and methodologies in machine learning, particularly focusing on coordinate descent methods, lifelong learning, and large language models. The authors discuss the efficiency of coordinate descent methods on huge-scale optimization problems, as well as the importance of choosing the right rule for faster convergence. They also delve into the concept of lifelong learning, which aims to enable machines to learn continuously from new data without forgetting previous knowledge. The paper highlights several key findings and novel ideas in the field of machine learning. For instance, it discusses the role of task-specific skill localization in fine-tuned language models and the impact of scale on catastrophic forgetting in neural networks. It also explores different approaches to overcoming catastrophic forgetting, such as experience replay and orthogonal subspace learning. Furthermore, the authors discuss the importance of benchmarks for continual learning in large language models, such as the trace benchmark, and various paradigms for efficient meta-lifelong learning with limited memory. They also touch upon the concept of dynamic growth for instruction tuning data curation and the use of synaptic intelligence for continual learning. In terms of algorithms and mathematical concepts, the paper explains the iteration complexity of randomized block coordinate descent methods for minimizing a composite function and the convergence of a block coordinate descent method for non-differentiable minimization. It also details the use of gradient core set-based replay buffer selection for continual learning and the application of sketching for communication-efficient federated learning. Overall, the paper provides a detailed analysis of the current state of the art in machine learning, with a focus on coordinate descent methods, lifelong learning, and large language models. It highlights the challenges and opportunities in these areas and presents several novel ideas and methodologies for advancing the field. Here is a combined summary of pages 19 and 20 of the research paper. The authors reference two papers: Atom Can Converge Without Any Modification on Update Rules, by Zhang et al., and Model Tailor, Mitigating Catastrophic Forgetting in Multimodal Large Language Models, by Zhu et al. The authors then provide a proof of Theorem 1, which involves defining a norm parallel top alpha % in ROAD. This norm is defined as parallel z parallel top alpha % equals z circled dot operator s parallel 2, where s is a vector that filters out the top alpha % of the entries in Z. The authors show that this norm satisfies the properties of a norm, including positivity, homogeneity, and the triangle inequality. The proof of Theorem 1 relies on the definition of the norm parallel top alpha % and the properties of the filter S. The authors show that the update rule of the MoFO algorithm can be written as theta t plus 1 minus theta t equals minus eta tmth circled dot operator filter t, where filter t is equivalent to the filter s. The authors also define a greedy filter, which is used to filter out the top alpha% of the entries in a vector. They show that this filter satisfies certain properties, including the fact that it is a norm. The proof of Theorem 1 is based on the definition of the norm parallel top alpha% and the properties of the filter S. The authors show that the update rule of the MoFO algorithm can be written in terms of this norm, and that it satisfies certain properties. The authors also provide a lemma, which shows that the norm parallel top alpha% is indeed a norm. This lemma is used in the proof of Theorem 1. Overall, the authors provide a detailed proof of Theorem 1, which relies on the definition of the norm parallel top alpha% and the properties of the filter S. They also provide a lemma that shows that this norm is indeed a norm. The paper discusses the optimization of a machine learning model's parameters using gradient descent with a novel approach called MoFO, which stands for model-free optimization. This method is designed to improve the efficiency and effectiveness of gradient descent by dynamically adjusting the learning rate based on the norm of the gradient. The authors provide a mathematical derivation of MoFO, showing how it can be used to minimize the objective function L, theta, in an optimization problem. The key idea behind MoFO is to adjust the learning rate at each iteration t based on the norm of the gradient gt. Specifically, the learning rate is set to be proportional to the inverse of the norm of the gradient, with a parameter alpha controlling the proportionality constant. This allows the learning rate to adapt dynamically to the size of the gradient, which can help in avoiding large updates when the gradient is very large. The authors also provide an analysis of the convergence properties of MoFO, showing that it converges to a local minimum under certain conditions. They compare MoFO with other optimization algorithms such as stochastic gradient descent, SGD, and ATOM, and demonstrate its effectiveness in various experiments. In addition to the theoretical analysis, the paper presents several experimental results using MoFO for fine-tuning pre-trained language models on different datasets. The authors show that MoFO outperforms other optimization algorithms in terms of performance and efficiency, especially when fine-tuning large models. The implementation details for these experiments are also provided, including the specific hyperparameters used for each dataset and the computational resources required. Overall, the paper presents a novel optimization algorithm that can be useful for improving the efficiency and effectiveness of machine learning model training.